Good afternoon. Today is our second interview for the HAO director position. The person interviewed is Sarah Gibson, who again is familiar to you. So I'm the one who needs to read. You probably know this better than I do. I will start by stating her degrees: 1989, Bachelor of Science in Physics, Stanford University, Stanford, California; 93, Master of Science from the University of Colorado, Boulder; and 1995, PhD, both of Master and PhD in Astrophysics from the University of Colorado, Boulder. After the PhD, Sarah came to HAO. That was the first professional appointment after getting her PhD, and she spent a year with you as a postdoctoral scientist, and then went on to NASA Goddard Space Flight Center as an NRC associate. I think she won that funding. That's a position for which one has to write a proposal and obtain the funding. So that was her first successful funding. The research assistant professor at the Catholic University of America. She started after that with that appointment in '98. She interrupted it for a while to go to the University of Cambridge on another postdoctoral fellowships, this one from NSF NATO, and Department of Applied Mathematics and Theoretical Physics. She came back to her position at the Catholic University of America for one more year before coming back to HAO in 2001 as a visiting scientist. And after that followed a series of scientific appointments in HAO as Scientist 1, Scientist 2, Scientist 3, and Scientist 4, which we became in 2012. In 2011, I won't go over all the professional appointments, but in 2011, she became the section head of the long-term solar variability section, and which is she is heading as of today. She is published. She's a well-published research scientist with close to 50 papers to her name. She has also been very engaged professionally in the scientific community with a number of service roles on the boards and advisory bodies with NASA, with NSF, and most recently as the contributor to the Decadal Survey. With much further ado, I turn the stage on to you. The next 45 minutes is allotted to the presentation, following by the Q&A period of about 30 minutes.
All right, thank you very much, Vanda, and thank you all for coming. I'm going to keep the light off up here, I think, because I think you'll be able to see some of the rather interesting images that I'll show better with it that way. You may have wondered the second part of my title, Seeking the Spheres to Connect Them, which sounds like something Yoda might say, and it's because it's a line from a poem by Walt Whitman, and at the end of my talk I'll put it up for you to see, and it's curiously apt to the question of how magnetism connects the sun and the earth, and you'll see that shortly. And when I see this and I talk about spheres, I'm not just talking about spheres like the sphere of the sun and the sphere of the earth, but I'm talking about the layers of the atmosphere in the sun. And I'm talking about the space environment, the magnetosphere. And I'm talking about the layers of the atmosphere of the earth. So I'm going to have three parts to my talk. The first one, I'm going to be talking about space weather and space climate and try to explain to you why I think they matter and what magnetism has to do with it. Then I'll talk about going towards a Sun-Earth system model and how would we do this and how do we develop long-term objectives and how do we overcome the sticking points that stop us. I'll give you a couple examples of those, but generally just give you an idea of my thinking of how to approach that kind of problem. And then finally I'll talk about the kind of place I think I'd like HAO to be, what kind of a workplace we are. And I was asked to balance my time between science and my vision for leadership. And so What I'll try to do is I'll actually weave them together a little bit. So for each of these three sections, I'll start with a vision statement and talk about how that then motivates the section to follow. So let me start with the first, space weather and space climate. And here the vision, I think, has to do with HAO as a part of NCAR. And in preparing for this talk and for just generally applying for this job, I went back and I read through some oral interviews of Walt Roberts, which were really interesting. And this was a quote I found I hadn't seen before. And he started out, he was asked the kind of age-old question about, are we, fundamental science or service, or are we doing, service? What is our role? And he started by saying, first and foremost, NCAR is a center for excellence. But he went on to say this. He said, science's ultimate justification is not truth, but usefulness. If it works, if it enables reproducible ways of making things that work, then it is good science. And I found this quite an appealing statement because it kind of reconciles that tension and justifies it as important, because it's not an either-or between basic science and service to society. Robert's statement is basically saying that useful science is, by definition, fundamental. And I would argue that fundamental science will always ultimately prove useful. So that brings us to the sun. And what should we be studying? And it's true, the sun can be studied as an astronomical body unto itself or in the context of other stars, and that's fascinating. But it's the connection to the sun to the Earth's environment that is most relevant to NCAR's mission, and in particular the betterment of life on Earth. So I would summarize by saying, we know that NCAR champions the science underlying weather and climate, and as the 21st century progresses, it's essential that through HAO, NCAR continues to also champion the science underlying space weather and space climate. Okay, space weather, what is it? And why does it matter to us here on Earth? Well, it matters to us because we are, in a sense, in the sun's outer atmosphere. The solar wind is moving through the heliosphere, and it's interacting with the Earth. And here this artist's conception is showing you magnetized plasma flowing past, and we have a shield. The Earth's magnetic field is acting as a shield against much of this solar wind. But it can't always, because when you have a particularly strong pulse of solar wind, magnetized field, particularly when it's pointing the opposite direction of the magnetic field at the front of the Earth's magnetic magnetosphere, it can drive storms, geomagnetic activity, including Aurora. So this is space weather. Well, Aurora are nice. Why should we worry about Aurora? And in fact, for millennia, really, we didn't have to worry about space weather. It was just a nice light show in the sky. But this is what the sun is sending our way. It's sending us light very quickly, about 8 minutes, and it's a spectrum, X-ray to radio. It's sending us that magnetized wind in the solar wind. And it's also sending us particle radiation. So there can be shocks and acceleration, and you can have energized particles that can impact the Earth. And the nature of these components is that the light has a base of total solar irradiance, which is almost constant in its brightness, but there is, especially in the short wavelengths, in the EUV and the soft X-ray, there's a very highly variable component. And in the magnetized wind, it's gusty. You can have storms. You can have fast streams of winds that hit the Earth. And in terms of energetic particles, again, that's very variable. And here's the impact at the Earth. And it's essentially the first effect, the light that comes comes at the speed of light, can cause immediate navigation issues. The magnetized wind takes longer. It can take 1 to 3 days, and that is what drives geomagnetic storms. It can cause problems with power grids and more navigation issues. And the radiation can arrive anywhere from tens of minutes to hours. And this can cause hazards to astronaut health, for example. The Earth's atmosphere protects us from most of this. So these are all three components of space weather that, honestly, the reason we're caring about them now is because we have technology, and we have power grids, and we have communication satellites, and we have astronauts in space. So let's start at the Earth, because that's where the space weather matters to us at the moment. If an astronaut was going to Mars, then we'd have to concern ourselves with that, but let's start at the Earth. Now, weather, of course, can range the gamut of something which happens fairly commonly. Rainstorms happen pretty often. Similarly, when you're lucky enough to be on the space station and looking out the window, you can see aurora like this on a relatively frequent basis, especially during solar maximum. But we can also have extraordinary weather. We can have superstorms. And of course, the Carrington event, which occurred in 1859, is the most popular of those. This particular painting is a nice one, and it shows some roughly contemporary, 1865. I did look into it, and it looks like it's actually of the North Sea. So here's what you need to imagine. So I don't think it's of the Carrington event. Imagine that island is Hawaii, and then you have the Carrington event. Aurora is going all the way south to Hawaii and Cuba. But as with terrestrial weather, we have to be able to understand and prepare for both the inconveniences that we routinely face, because they happen all the time, but also the extreme hazards that eventually we will have to face. Okay, so what makes up this space weather? Well, the first thing I'm going to talk about are the solar eruptions, the storms. And the good news is that as long as we have some sort of coronagraph observing, we often have a good warning that something's coming our way. We don't always have as nice a warning as this. This is a lovely composite. I'll start at the right. It's showing you a sort of an unwrapped image at the limb of the sun, moving out further and further out from the surface of the sun into a coronagraph. Here comes a gust. And then we have these heliospheric imagers, which were on board the stereo spacecraft, which are giving you the view sort of in a fisheye sense as you go even further out. And they were in a position where they could actually really monitor the whole sun-to-Earth event here. We could put, if we wanted to, if that was our priority, we could put spacecraft in a position where we could get images, movies like this all the time and know when you have something coming at the Earth. You can look, if you see that little monitor on the bottom left, when a pulse comes and hits the Earth, then the in situ, the spacecraft that's sitting just upstream of the Earth is measuring that pulse. So it's a really nice contextual view. The bad news is, with this kind of thing, it tells you something's coming. Maybe it tells you when it's going to arrive. We're getting better at telling when it's arrived, how fast it is. It doesn't tell you the magnetic orientation. And as I said earlier, it's that orientation which really makes a difference as to how big an effect a storm will have at the Earth. So, to get that magnetic orientation, we have to go back to the sun. And we know where they're coming from. They're coming from flares and coronal mass ejections. Coronal mass ejection is the image on the bottom left, and flare on the bottom right. The movie on the upper right, I guess I can use my pointer, is showing you both. There are two aspects of a single storm or release of energy. Just as in a terrestrial storm, you can have gusts of winds and you can have rain. They're manifestations of the storm. In a CME, in a flare, these are manifestations of a release of magnetic energy. And then you can see in this movie, there's a blob that goes out, and then after that, you'll see a brightening, which is the flare, and actually the energetic particles are what are impacting the spacecraft near the Earth at the end there. So, humor me here, I'm going to show you a backwards movie, because if energy is released, where does it come from? Here's a CME scene going backwards in time, back to where it came from. And a CME often has this elliptical cavity as part of it. And as you can see, the origins of this CME was very clearly in a cavity that was there before the eruption. This cavity, this dark circular structure seen in the sun's corona, is showing you a region with stored magnetic energy that can be tapped into to drive an eruption. And so this was a subject which I have worked on fairly comprehensively with a wonderful team of people over the last decade. And we set out to find out everything we could observationally about cavities and to try to test them with models and see what they told us. And what we found was that a model of the magnetic structure in the cavity of a flux rope, which is to say magnetic field that's winding around a central axis. It's a energetic, but it is a efficient way of storing energy. So it's a magnetic state which is really to be expected in a long-term equilibrium, because these cavities can last for days or even weeks before they erupt. So what we found was that the morphology, the shape of it, which is like sort of a hollow croissant, the substructure within the cavity, and quite interestingly, the flows within the cavity. Take a look just at this picture here. You see this bullseye. This is inside a cavity. And the reason this structure and this one are interesting, because in the model of a magnetic flux rope, there's nested cylinders or tori inside the flux rope. And if you're exciting or heating or causing flows along one of these surfaces, then you would expect to see this kind of structure. And then, finally, we had actual coronal magnetic measurements because we have the COMP telescope at Mauna Loa Solar Observatory. And we have measurements of linear polarization, which tells you about the direction of the magnetic field. And for the purpose of this talk, I just want to point out that what we have on the left is what we observe in a cavity, and on the right is what we expect to observe in this kind of polarization signal from a magnetic flux rope. So all of these things together tell us that what we're looking at is a magnetic flux rope. Why does that matter? Well, we've looked at cavities, and we've looked at what happens to them before they erupt. And what we found in a survey of about 100 cases was that when you have a small, squat cavity, it seems to be a pretty stable configuration. It's not likely to erupt in the next couple of days. We see these at the edge of the sun, and then they rotate around, and we stop seeing them until they get to the other side. So we were looking to see if there was an eruption within a couple of days of when we saw it at the limb. And when you get to where they look like sort of a circle, yeah, they're not. So here's the likelihood of erupting, 10% of these, 23% of these. But when you start to get a teardrop shape, it's a good bet that that thing is going to erupt within a day. And so this is not, you're not seeing it starting to move up, you're just seeing the shape, and you can say, this thing will erupt tomorrow. And the reason that's interesting is because in our models, we find that if you make a magnetic flux rope and you keep feeding it twisted magnetic fields, eventually you reach a point where current sheets build up underneath it, and reconnections happen, and the thing starts to very slowly grow to a kind of a teardrop shape. And once this happens in the simulations, it's like a lit fuse. Eventually, it's going to reach a point where it cannot keep stability, and it's going to erupt. So this is a clue. This is a way of predicting a CME before it happens, at least in cavities. So, at least for cavities, then, we're set, right? We know the pre-eruption magnetic structures of flux rope. We can model what kind of thing it happens in terms of an eruption, and then we can just propagate it out to the magnetosphere and model space weather, right? The trouble is, it's more complicated than that, because it's not just a matter of a flux rope in isolation. It turns out that the magnetic field around it, the context, both in time and space, affects the eruption. And the first thing we noticed with simulations was that sometimes, as it erupts, it might spin around. And it's not just simulations. Look on the left. If you watch this a few times, I think you'll see that the center of the structure is untwisting or something as it goes out. So remember, we're trying to figure out if this thing is pointing southward when it gets to the Earth. So if you have a really good model of the source region, and then as it erupts, it spins around, you've got it wrong. Well, maybe you can follow along in these observations. It's a good use of Mauna Loa chronographs to try to see what's happening, perhaps. But also, it can reconnect. It connect to the surrounding magnetic fields. And so, in fact, in our simulations, we found that this is what it was like before it erupted. This is what escaped into the solar wind. So not only had it rotated around, but it had actually, it had changed its magnetic topology. So it had connected with itself and with surrounding fields. So it was actually like a Spiramac-type magnetic structure in this simulation. And next, look what's left over. It didn't just kind of all together go out in an eruption. It pinched off behind and left a piece behind. So there was a piece of flux rope left behind. And that's interesting because if there's something left behind, it might erupt again, especially if you keep driving twisted flux into it. These are what are called sigmoids, which are also have been shown to be a signature of a magnetic flux rope. And a sigmoid transitioning to a cusp is what you expect in an eruption. And this particular region, in the course of a week or 10 days as it crossed the disk of the sun, erupted 4 times, over and over again. And in this simulation, recent simulation, we see that that if you have one structure, if you have a flux rope erupt and then the same region erupt again soon thereafter, the first one can act like a snowplow and pave the way so that the next one goes really, really fast, catches up, hits it. When you start interacting CMEs, you start building up shocks, energetic particles, and these have been dubbed cannibal CMEs. And there's more. It's even more complicated because maybe you can predict the eruption of a flux rope because you saw that it was getting near an instability, but its eruption might trigger a nearby eruption. And simulations have shown that the eruption of one rope can affect what's on top of the other one. So it was stable before, and you wouldn't be able to predict it by one of my tear-shaped arguments. It changed the environment, and now it erupts. So the take-home message is it's not enough to know just the local coronal magnetic field of the source region. You have to know what's around it, and you have to probably model it to find out what's going to happen and what's coming at you at the Earth. Okay, so now let's talk about a different kind of space weather. This was a storm-driven, but that global magnetic field, the full 3D field, matters also for the structure of the solar wind, and that can drive space weather as well. And it's particularly easy to see that when you turn the button off on activity. And so at solar minimum, in the sunspot cycle, we wax and wane from lots of sunspots down to very few at solar minimum. And eruptions, CMEs, flares, they correlate with sunspots. So if you don't have any sunspots, you don't have any CMEs, you don't have that kind of space weather. And now you can just look at the question of structure. And in 1996, this was what the global magnetic structure essentially looked like. And this is what the solar wind looks like. And let me explain this. What we're looking at is time on the bottom. So it's going through essentially so it's a year's worth of data, basically. And in this axis, we're going from pole to equator to pole. Blue is fast, red is slow. So what we're seeing is slow wind at the equator and fast wind at the pole. And this is kind of our canonical picture of what a dipole magnetic field emitting fast solar wind through these open field lines, which is where the solar wind comes from. That's what we expect to happen. In 2008, the sunspot number was essentially the same as in 1996, but we had a whole lot more structure. And so we had open field like this near the equator. And the solar wind during this time period was similarly more complicated. So instead of just being simple blue, fast at the poles and slow at the equator, you had some slow wind going up to very high latitudes, and you had fast wind at the equator. And equator matters because that's where we are. So this is what's driving the Earth's space weather. And so we tracked, here's one particular one of these fast wind streams, they're called. And this is what they look like at the sun. It's a coronal hole, so it's open magnetic field. Here it is in the solar wind. So you had fast solar wind pulse coming through. It affected the geomagnetic field and the auroral indices. These values are actually kind of on the low side. This is not the kind of big auroral power that you see in a CME, but it's very clean, periodic, and that definitely was that there's a pulse that comes with it. The Earth's radiation belt also reacts to these fast solar wind streams. It actually first empties them and then fills them up again. So you see this green bump and this green bump are associated with the fast solar wind stream. And even the Earth's upper atmosphere, the thermosphere, is reacting to these fast solar wind streams. And so you can see the fast solar wind streams and the magnetic field within them is causing a signal in the thermosphere. And the thing is, this structure, this is not something like a CME that comes and goes. This particular structure lasted for several months in a row. So for month after month after month, it's like a lighthouse beaming around. We got hit, and again, and again, and again, month after month. And it's because the magnetic structure at the sun did not change much. This is showing you the magnetic structure. This is essentially the warp in that equatorial region at the sun of the magnetic field. Here's pulses of velocity. And down here, we have pulses in geomagnetic field. And in analyzing this in the context of a geomagnetic record going back 150 years, the periodic behavior was unusual. There was nothing quite like it. And it wasn't that there wasn't periodic behavior in other solar cycles, but it was that there was periodic behavior at the same time there was no activity. Because if you have a lot of activity in CMEs, it messes up the signal. So this was unusual in that way. And that periodic behavior also showed up in the upper atmosphere and in galactic cosmic rays. So the global magnetic field affects the heliosphere and through that space weather at the Earth. Okay, what about space climate? Now, I have to start with a definition because this is one of those phrases which is used in different ways by different people. I'm going to use it in a fairly broad way. First of all, very simply, you have space weather. It varies over solar cycle timescales, and the long-term variation and longer timescales, that long-term variation is a space climate. Second of all, the sun is changing over the solar cycle, as I'll show you in a moment, and this can have an effect on terrestrial climate. And how big of an effect is the question. But that question of how much variation how much the variation in the sun affects the climate at the Earth is something which is part of space climate. The couplings between, because you can't study these in complete isolation. Space climate can affect terrestrial climate and vice versa, and so that's something that has to be considered. So what do I mean by long-term variation? Everything from solar cycle to millennia. Here are the inputs into the Earth's environment in terms of solar cycle, and it's it's a little bit reductionist to break them into these two, but they give us a good idea, flavor of what's going on. So the first thing is particles. And here I'm including two kinds of space weather that I had before. One of them is the magnetized wind, and the other is the energetic particles. Okay, the yellow is the sunspot cycle, and the red is the geomagnetic response. So at first glance, it looks like, yes, when you have a maximum, or when it's modulated, they're basically going to some extent in phase. So geomagnetic activity is following solar activity, which we kind of expect because of the reasons I just gave you about how space weather drives geomagnetic activity. But it's not quite so simple. If you look carefully, you'll see sometimes there's two bumps here, and a lot of times it's lagging. It's a little bit later. The red is a little shifted relative to the yellow. And that's because the yellow sunspots are really telling you about these storms, the CMEs and the flares, and the geomagnetic activity associated with those. But at the same time, we have structural changes. This is a nice movie. Just the sense here to get is it goes from simple to complicated. At solar maximum, the structure in the heliosphere is just very complicated. It's not simply just slow wind at the equator and fast wind at the poles. It's all over the place. This was where we ended up in 2008, where it's simpler, but there's still some structure. And that kind of, the fast winds that you can see sort of in this structure, can drive geomagnetic activity. And that tends to happen in the declining phase of the solar cycle, which is why this gets shifted a little bit to the right. So the long-term variation of the heliospheric magnetic structure and activity affects energetic particles, geomagnetic activity, galactic cosmic rays. We also have variation in the radiation. Now, when we're talking about total solar irradiance, we're talking about very, very small amounts. This is the solar cycle modulation of the total solar irradiance, and it looks big because it's been zoomed in, but this number is very large here. And so what we're looking at is about 0.1% from maximum to minimum. So it's not a big effect in the first place, the modulation of the total solar irradiance with solar cycle, although it's there. If, however, you look in the short wavelengths, and I've already talked about how the short wavelengths can have a greater modulation, it becomes much bigger. And the difference from minimum to maximum can be on order of magnitude, or factor of 2. And this sensitivity is passed down to the upper atmosphere of the sun, of the Earth. So the thermosphere has a modulation which is clearly in phase with the solar cycle, and it can be modulated by much bigger factors. Now we're talking more like an order of magnitude. Now, I said it's a little bit reductionist to break it into these two things. I've already talked about how the thermosphere responds to geomagnetic forcing and the particulate forcing. But this behavior is predominantly driven by radiation and by the short wavelengths, the ultraviolet, extreme ultraviolet. And here in the thermosphere, you can see that this recent minimum was at a lower level than previous minima, and lower than what you would expect from anthropogenic change. So that brings me to my next subject, extreme scenarios, and in particular, grand minima. Now, sunspots have been going along quite nicely over the last couple hundred years, and we see them going in an essentially 11-year cycle. But there was a time period in the 17th century when there was about 6 or 7 decades with essentially no sunspots, the Maunder minimum. And the question of why that happens is a fundamental question of dynamo theory, which I won't go into today. Now, what would a Maunder minimum be like for space climate if we had one? We can get some insight from the recent minimum, perhaps. And here's an interesting thing. This was 1996. I already showed you this. Fairly simple. 2008, more structure. A year later, in 2009, the sunspots did not pick up. There wasn't really any significant flux emergence. So the sunspot number does not change much from one to the other, but the structure changed quite a bit. This is 2009. The magnetic field on the surface has essentially diffused. The structure has melted away. This may be what a Maunder minimum would look like if you didn't have sunspots. So what would the implication be? Well, at this time period, we had the interplanetary magnetic field, the blue. So the black is the sunspot. You can see the sunspot bottoms out at 0. You can't get less than that. So we sort of stopped getting information from it about 2008. But the interplanetary magnetic field kept going down. The cosmic rays, the galactic cosmic rays I was mentioning, are modulated by the interplanetary magnetic field. They reached all-time highs. They got to this point in 2008, and then they went up again in 2009 when this structure changed. And radiation belts similarly showed a big change, in this case, an all-time space age low. What about radiative drivers if we had something like this? So this is I'll get back to this. This is one of our sticking points. Now, it's not completely hopeless, but there is an open question here because we have some guidance from stellar observations which give us limits on what kind of variation we'd expect. And we also have quiet sun modeling, as shown here, which we can use to get limits. And these are telling us that, again, the total solar irradiance is not likely to have a big change. 0.25%, which is probably a reasonable amount to assume that the total brightness would change in this kind of sustained solar minimum. But the short wavelengths, the ultraviolet and extreme ultraviolets, might vary a lot more because they depend on the magnetic field. And if you turn off the magnetic field, they're going to notice, they're going to respond. I'm going to come back to that actually shortly, but first, let me get on to my next section, which has to do with the Sun-Earth system modeling. And there, I think the vision has to do with HAO in the context of a broader community, solar and space physics. So what is our community? What is solar and space physics, sometimes also called heliophysics? What is that? It's a domain that includes the sun, connections outward to the solar wind, interactions with the terrestrial magnetosphere, couplings between the Earth's atmosphere and its space environment. We have a challenge or an opportunity for our field, which is to become a truly integrated field and address this system as a whole. And we talk about this a lot in our field, and I think we've made some real steps, and we're starting to really understand the components and how they relate. But there's more to be done, and to really have a coherent form, I think we have an opportunity here at HAO. Because number one, we have most of these fields represented with the staff at HAO, and in particular through the collaborations with the broader community. And we have NCAR. We're part of NCAR. So we can really look from the sun to the mud. And we can really play a big role in conceptualizing and developing the next generation Sun-Earth system community models. This is now almost a direct quote out of the GeoVision. And I liked that they said conceptualizing, developing. I don't think we're ready to start completely building these models and using them there's a lot of sticking points I'm going to get to along the way that we have to address before we can really, really have a Sun-Earth system community model. And that's what I'm going to talk about now. I'm going to give two examples. There are a lot more. I mentioned the solar dynamo as one of them. There's issues of the coupling of the lower and the upper atmosphere of the Earth, which have long-term objectives and sticking points associated with them. I'm going to give you two examples today in the interest of time. The first is space climate. So here's our long-term objective. We need to understand how extremes of solar variability affect climate. And there was this work previously done by Emil, which took a very reasonable number, 0.25%, in total solar radiance and said, what would happen if we had an extended period with that kind of decrease in total solar radiance? What would that do to our climate models? And in particular, would it slow down global warming? And what he found was, well, at first there would be a reaction to it, but eventually, so the yellow is if you ran it without that sudden knockout of the decrease in the solar signal, and the blue is if you turn it on. Here's our Maunder minimum type thing. And what would happen is that eventually it caught up. And that's an important result. Now, there is an open question, though, because especially in the Earth's upper atmosphere, there's a sensitivity to the short wavelengths. And we don't, that's my question marks before, we don't really know what the likely variation of spectral irradiance, meaning not just the total irradiance, but also the irradiance in the ultraviolet and the extreme ultraviolet is. And then what would the implications for climate and also space climate be as a function of height and as a function of region? So here's a roadmap. This is just a layout straw man, if you will, is to start with a high-resolution radiative MHD simulation, to do spectral synthesis, to actually come up using radiated MHD, solving radiative MHD equations, and come up with a spectrum, test it and calibrate it using modern data, and come up with, for example, predictions for a Maunder-type minimum and put them into the climate models at NCAR. All right, here's my next subject, space weather. Long-term objective. We want to know if a CME, a storm coming that we see and we get 2 days notice so we can do something about, is it going to matter? It's almost as well. It's definitely bad to give false positives, right? We don't want to tell people that there's going to be a huge storm and then have it be a dud every time. So we need to do this right. There's my picture. The sticking point. What is that internal magnetic field? We don't really know. And in particular, to solve that, we have to get knowledge of the source region and the global coronal magnetic field. So how do we do that? All right, so here's a roadmap. And this is the outline essentially of a project that I'm putting together now for the next 5 years, and we're going to test this out. And the idea is to start with an initial guess magnetic field, forward model or synthesize observables at a range of wavelengths that would go along with that magnetic field, compare it to data, or, in fact, as we get started, we will come up with a sort of a synthetic testbed type thing, a model generated to test our methods, and add currents until we match the data, and develop optimization strategies. This is in collaboration with CISL for fitting model to data, taking advantage of the sensitivities of the different observations. And here's where having a test bed, a fake synthetic model to work with comes in handy. We can generate any kind of observation you can imagine before we even have the telescopes. And we can then do statistical methods to design and choose between measurement strategies. We can really test what wavelengths are the ones that we should focus our energy on and what kinds of observations. And this is very important for the design and the progress and the ultimate utilization of the data from the Cosmo telescope. All right, my last section. HAO is a healthy workplace. And when I thought about this and what I wanted in terms of a place to work, I came up with 3 things. We need to be collaborative, and I mean that, first of all, in terms of what we've already started to do, I think, in collaborating across the sections within HAO. These questions of space weather and space climate, these long-term objectives cannot be done by any one section within HAO. But I also mean in terms of the collaboration with colleagues outside and inside NCAR. And this is a way that we can really span the solar system with a set of long-term objectives. We need to be forward-thinking. We have to be thinking about the future and who's going to succeed us and what's, training the future workforce. And for that, we need to mentor and seek a diverse group of early career scientists. And in the diversity, of course, is what really fosters originality and innovation in different approaches of doing research. And we need to be engaged. We need to have active discussion and debate among the staff and with our external advisory committees in order to come up with something that we all kind of stand behind. We don't have to work in lockstep, like all towards one goal. Everybody does their own little compartmentalized thing. But it's good if we actually agree on why we're doing something, why we're doing some sort of big problem. And then when we have those goals and priorities, I think it's the role primarily of the HAO director, but also of the staff, to communicate and advocate this to funding agencies and to the general public, get people interested in these problems. So I'm going to go through those 3 things and give you some fairly concrete examples from my own experience or thoughts. First of all, is strengthening ties between NCAR labs. And first of all, the Sun-Earth system is an obvious thing where we can connect to NESL, obviously, maybe also to RAL. Data assimilation, we're already connecting to CISL, and with our the statistical methods for the project I talked about. And maybe we can do more in terms of data pipelining and archiving with CISL. EOL, we have a proposal in the works, I think, to do an eclipse study on the G5 airplane. So we can collaborate within NCAR. We need to work with the university and broader community. And this means, we can do things like join in, participate in the campaigns and the meetings with SHINE, GEM, and CEDAR that NSF runs. My own experience has been with the whole Sun Month and the whole Heliosphere interval, which was essentially providing a rallying point, a time period to study from Sun to Earth. And we had hundreds of scientists involved and something like 80 publications that came out of these campaigns. ISSI. I've had I've enjoyed very much leading 2 ISSI groups. These are more targeted, 12 people with a particular problem to solve, and this is another way of doing a collaboration. We can reach out to our IAU, SPD, AGU, through meetings, through interactions. We have some friends in town. We have the National Solar Observatory. We have NOAA, the Space Weather Prediction Center. We can strengthen those ties. And of course, we can connect to the universities through teaching and UVisit. Forward thinking. As I said, this is really training the future workforce. I gathered some of the pictures of the students and the postdocs that I've been happy to work with over the last few years. And it has been a real learning experience for me to work with these young people because they're all different. They come from a real range of countries and backgrounds. And so they all are different from one another, and they have different learning, communication, research styles. And so I learned a lot by essentially listening to them, adjusting the way I interacted based on how they interacted best. And I think this is an important way to interact in general. And we have to do more in terms of actively pursuing diversity. These are a couple programs that I've had some contact with, these two more comprehensively. Both of these target middle school students. And both of these, the way they work is they have female scientists being the ones who answer questions and who interact or present labs. The I Have Dreams Foundation, I only have a small interaction with. I did a Meet the Scientists sort of thing, but it's an interesting foundation that targets low-income students in the Boulder County area. There's a lot we can do to try to get people at that critical time, middle school, when we can get them to go into our field. Or at least just get interested in it so it becomes something that they're excited about in their future lives. Engaged. And this is where my interaction with the staff comes in. I actually love a good argument. I really do. I think it's because I don't get angry or anything. I just enjoy taking 2 points of view and trying to really see what the last one standing is. And what usually ends up happening is that both points of view get modified to some extent. And I think this can be very fruitful. Not everybody interacts this way. So I think more specifically, I think it's critical for a director to listen to and consider all points of view. Ultimately, the director has to make a decision, but it has to be an informed decision. And the staff should understand why it was made in the end because of the discussion and the debate that happens in between the engaged workforce. Not everybody has to argue, but I personally would want a staff that challenges me and makes me defend a point of view. This particular picture is from one of my ISSE groups, and we were on a walk, and we came to this signpost, and we were going to a park. Both signposts point to the park. So we had a very kind of long and engaged discussion about, which way should we go? And we talked about all the different things, got out our phones and so on. So that was our little discussion, which way to go. And as I said, the director then has to take what they learn, what they assess from the staff, what they learn from their communications, and advocate to funders, and to continue to play a role in setting national priorities. And this is something that I've been involved in through various committees. Okay, now I'm ready to summarize. I think I'm okay for time? Good. First, this is now summarizing these points. First and foremost, as a director, this is what I would do. I would try to enable useful science. With the staff, I would try to identify where we want to go, what steps must be taken to get there, and how to overcome the sticking points, the things that are impeding progress along the way. And then work across NCAR and with the community, train a diverse future workforce, and actively listen to staff, and advocate to funders and the public. And finally, and this is sort of a personal pledge, if you can see it, combine poetry with pragmatism. And I think this is important. Honestly, a measure of success as a director, and I realize this is an ambitious goal, but if the members of the staff were to go home every day and think, I got something done today, and it was significant, and it was fun, then that would be success. So here's my poem to end on. It's kind of eerie, launching forth filament out of itself, like the sun. And here it is, across the oceans of space, seeking the spheres to connect them. So that was my inspiration.
At this point, I would like to open for discussion. And yes, could you please do that little part? The rest is for the audience to do some work here. So I'm looking for the first hands up and the first question. After that, it becomes easier.
I'll do it again.
Okay. Thank you, Joanne.
Sarah, you're very aware of the funding challenges that we have. And I'm wondering, from your standpoint, what is the best way to build HAO? Is it through, for example, many awards, many grants, or would you want to try to see how we can combine efforts to, really build on our base? What is your thinking on soft money and HAO?
Right. Well, I think the first step for much of what I talked about here is I think we have to have a staff retreat, and we have to set our priorities and decide what are these long-term objectives, what we think we have to focus our efforts on. And then, at that point, we have to step back and do a reality check about funding and what can we afford to do. And then we can ask, okay, well, see, the thing is, by doing that planning first, you build a really compelling case. You come up with a reason you want to do it, and you come up with why each step along the way is needed, and then you go and actively pursue funding specific to the particular steps. I do think we need to have a more coherent lab-wide discussion about how we go after the soft funding, because it's really, really hard now, as people know, and it's a lot of effort. We spend a lot of time writing proposals. I think ultimately, though, we have to set ourselves a roadmap of where we want to go, and then try to seek how we're going to get the money to do it. Hmm. Yeah.
Hi. What can you do for HAO that the other candidates cannot?
Well, first of all, I want to say that I think both of them are very good, very strong candidates, and no matter what happens, I'm going to be happy to work with them. But I think I'm the best for the job. I think I have a management style that will be very listen to the staff. I think I can mediate conflict. I think I have the energy and the enthusiasm to go out there and advocate for HAO. And I think I've been thinking about this a lot, and in the context of national policy, national planning over the last few years, and I think that insight will be valuable for HAO.
Thank you.
Other questions? Okay, so the microphone makes its way back.
I have a question on your science roadmap.
Yeah.
Can you go back? You
Sure.
had a couple of nice examples about the roadmap. So, for instance, you start with Matthias's model,
Yep.
and you want to try to determine what the solar wind variation in irradiance might be.
Yeah.
And you're going to try to compare that to existing observations. But then you mentioned then you're going to go to a Maunder minimum. How do you do that? How do you go?
Well, sorry, I kind of went through it fast. This particular case, because I think it's a fairly well-developed thought. I mean, there are other, for instance, space climate and how it's forced by solar wind is something I'm personally very interested in. The idea here is to use the quiet sun to get a sense of what a Maunder minimum might be like, and to build a spectral synthesis as a first step. So that's the idea, is that you maybe don't have sunspots, and if you have a quiet sun all over the sun during a Maunder minimum, what would that do to the spectrum?
That's assuming the quiet sun's not changing.
Yeah, absolutely. But you can take some extremes. I mean, for one thing, you can turn the magnetic field completely off or down, and this has a huge effect on the chromosphere and the corona, and therefore on the ultraviolet, extreme ultraviolet. If you turn the magnetic field completely off, the total solar radiance is not going to hugely change. But if you turn the magnetic field off completely, it does affect the upper atmosphere, and therefore the short wavelengths which affect the terrestrial upper atmosphere. There'd be a strong effect. So we could push it in some very extreme sense that way.
What are your ideas for recruiting and retaining diversity in your staff?
Yeah, so that comes back again to my own experience, which is really trying to be open to a broad range of approaches, and providing a welcoming environment where people feel, young people in particular, that even though they may not be like the majority of the people in the room, their approach and their background is valued and, in fact, embraced, because it brings a new perspective. I think it's very easy, all of us do this, it's very easy to kind of fall into the way that we're used to doing things. And by opening ourselves up to different approaches and taking time to really listen to what people have to say about how they do science and how they also communicate, I think that helps build an environment that people want to be at. And then the second part is outreach, getting out there, especially to students, and especially to students, minorities, young girls in middle school, and indeed people who don't have opportunities.
How do you recruit for candidates for jobs?
Yeah. One of the best things, I think, is to go to the historically minority schools, black schools, for example. There are meetings that you can go and specifically target students that way.
Sarah, how do you how do you identify the idea makers within HAO in the bigger, community? How do you identify them?
Oh, it's so easy. Come on, the ideas are popping out of their head left and right. And so I think we see there are idea makers all over, and we should listen to them and test the idea. And then there's two parts, right? You have to have these exciting ideas. And I like coming up with all sorts of grand plans and schemes and paths and so on. It needs to be tested by debate and argument and held up to scrutiny and challenged. That's a really essential part.
Both parts of the talk, the themes were interweaved, so both science, you can ask questions of management, vision, science. Well, can you talk about what you think are the biggest challenges? Microphone, please.
What do you think are the biggest challenges that you face, or that any new director is going to face?
So I think the first challenge as a new director would be, for me, would be to understand what's going on in NCAR and in the management of NCAR and how the labs, how things work. I think that's an important first step to take to see how HAO fits in. I think the next challenge is to get out there with the staff and to have a retreat and make sure that we have an actively engaged discussion. I think that's very important. And then get out to the community. And at that point, if we've done it right, we will have some long-term objectives that we can stand behind and start getting, and we want to communicate those and see if they stand the challenge of community discussion. And then we need to advocate. So those are the challenges. Advocate and get more resources for ourselves and for the community. Because if we have a good idea and we sell it well, it helps everybody.
One more hand goes up. She answered my question. Okay. Michael has a question.
Now, in the years where the U.S. funding was on pretty much a constant decline, at least what trickled down to HAO, it was an important component of the program that we had strong international collaborations where actually funding for solar and solar terrestrial research was increasing quite a bit. Would you comment on the international collaboration future?
Sure. With regards to space climate in particular, there's a very much an international interest in that. SCOSTEP is a program international program loosely affiliated with COSPAR, and they have a new program called Varsity. And we were involved in giving our information about space climate, our thoughts on that, to the group that then successfully proposed. I've been in contact with these people, and I think we can work with them to do some community-type workshops. So that's one opportunity. The International Astronomical Union, I'm on the steering committee for the Solar and Heliospheric division, and there's a shuffle right now. They're making new commissions, which are the next section down, and so people have to propose, and that's something again where space climate and space weather are being put forward through the International Astronomical Union, and so yes, I think the links are there, and we can continue to pursue them, and then of course through our visitor program, and we do have we're starting a collaboration with through the COST program in Europe with Silvano Fineschi to try to connect our Coronal, the COMP telescope, and with the COMP in Slovakia, with the telescopes that Silvano has in Slovakia, and so on, and the efforts there, and the planning for coronal magnetic fields. Coronal magnetic fields is something which I think is probably going to take an international effort to, certainly for a space mission. China is building a Cosmo and is building a radio telescope like Phaser. So coronal magnetism, there's a huge connection to China. India is building a telescope, and they are going to have, this is new, they just this I just found out at COSPAR, they're going to have an instrument like the Solar C in Hawaii, which is like COMP type measurements, coronal magnetic fields, but with a spectrum and a smaller field of view. So there's going to be some exciting new observations that will require international collaboration.
It's again related to the severe shortage of federal funding for research. I used to wonder whether there could be an institute which can employ its own scientists full-time with its own funding, rather than depending on federal funding. So, which means you have to raise your own money. Is that something considerable, or
in the future, it may, for our field, I think once we get past some of the sticking points of science for space weather and it becomes a more economically viable option, there may be ways to fund space weather science as it applies to applications in use, because there are people out there who need that kind of work. At the moment, what we're doing here at HAO really is the basic science that underlies these kinds of things, and as such, it's harder to get somebody to pay you for it. Sometimes I suppose you can get, the big telescopes can sometimes get someone to get their name on a telescope and get a grant. But I think our federal, the NSF, it's part of their mission to fund this kind of science. And so it's appropriate that we depend on them and on the other institutions or the agencies like NASA.
Hi, Sarah. I may not describe this perfectly well, so stop me if I don't seem to make any sense. We had a very interesting talk this morning about flex ropes. Yeah. And it was, sorry you missed it. It was really cool.
I'm sorry, too.
And then you mentioned today is that we don't understand really the direction of the interplanetary magnetic field.
Yeah.
So if we did have enough information on the sun with understanding exactly where the magnetic fields are and understanding a whole lot better how those flux ropes erupt, do you think we could understand the interplanetary magnetic field better?
Yep, that was a very clear question. Yeah, I agree. Yes, I do. And here's how I can see it panning out. And this may not be for a while, though, because we have to solve these sticking point basic questions. I mean, some of this, there's discovery science still to be done. Here's how it could pan out. If we have a 3D coronal magnetic field, a good representation of it, and we take yesterday's field, and we look at today, and we synthesize what all our observations, we've already identified what the perfect set of observations are for really constraining the problem, and we adapt our model until it now matches today's observations, and then we shake it, we kick it, we put flux in from the bottom, we let it, we run through an ensemble of scenarios, and we come up with a probabilistic forecast of whether it's going to erupt and what it's going to do when it erupts. We then put that into a model of, in the heliosphere, moving out to the Earth. We can do data assimilation to use the observations we have as it goes and to update and improve and choose between, narrow in on that ensemble of possibilities. And yeah, I think we can do a good job of saying what the magnetic field is at the Earth when it gets here in advance and make some good choices. And there are a lot of sticking points along the way that we have to get through first.
I'll continue on the vein of the science.
Sure.
So predicting the CMEs is something that is possible, maybe even probable in the foreseeable future. But the prediction of flares, of eruptions of the radiative nature that are, as you told us, have more instantaneous effects, or not quite instantaneous, but certainly a lot faster.
Right.
What do you see for our ability to predict those kinds of phenomena?
So I think we can do that too, but it's harder and it's one step down the road. So the first step is to use all our observations, come up the coronal field, and especially if you have an eruption, now you can go through all the possibilities of how it erupted to get your magnetic field and do the sort of thing I talked about. But actually what I said applies to what you're talking about too. Because if we have today's magnetic field, we can run, we don't know, if there's going to be a flux emergence over here, or if this is going to erupt and then bump into that and make it erupt. But we can run simulations, all the possibilities, and come up with an ensemble of possibilities, and we can get a likelihood. So, for example, if you have no active regions, no sunspots on the sun at all, your probability of a flare is way down. And so that's what we can do now. But we can do a little bit more. We can maybe look at these sigmoid structures and say this is built up energy. It's got to release eventually. But to really say something's going to happen in the next short term, then I think you have to have big supercomputers crunching the simulations. I think that's how you do it. And you can maybe use observations below the surface of the sun to tell you that something's likely to push that particular area, which will help you be a little bit more choosy in how you run it and how you weight your ensemble. But I think it can be done too.
And how about the dynamics in the interplanetary medium as it traverses? Even though you have a good knowledge of the coronal magnetic field, there can be an infinite number of possibilities of the dynamics.
It's a very good point. I mean, one thing you have on your side is if you're running these, I'm talking about some big computers here, but you know what happened yesterday, right? It's not infinite possibilities. So you could be running an ongoing solar wind model, so you know what it's likely to run into. And you can use data assimilation. If you have telescopes like that nice movie that Craig and others put together with the heliospheric imagers, if you have those imagers sitting there all the time, if your simulation is saying it's going this way and those are showing you it's going a different way, you now can choose between your simulations and come up with a better prediction.
Does it give any indication of the magnetic field?
For that, you're going to have to depend on that origins of the sun. I don't, unless we come up with some sort of solar telescopes that fly deeper into the solar wind and sample in advance, and they could again be used assimilatively to update.
My question is particularly with reference to the BZ that causes, how to predict the BZ at Earth. Even though you have you can compute the weak BZ at the corona. How do you compute or predict the actual BZ at Earth?
The actual direction. I'm presupposing a lot of things here. I'm presupposing a really big computer, and I'm presupposing some very good models. And very effective use of data, a range of data. But if you have that simulation, if you've run the simulation right, and you have the magnetic structure right at the sun, and you propagate it right and interact it right in the solar wind, then that's how you would come up with a prediction.
Hi, sir. I'm an external person, as you know. Can I ask a question also? Okay. You have been mentioning a lot about modeling. How about instruments? For example, the Cosmo, it's an instrument to measure coronal magnetic field. I think, it's a key to understand the sort of physics, the prediction.
Yes.
For the future.
Absolutely.
But what's your plan? Any idea to move forward with this Cosmo project, get a funding? And also, as for ground instrumentation, also, do you have any plan for the future space missions for involving the NCAR? Okay. So HAO.
Very good question. And everything I just said would fall flat on its face without observations. There is no way we would get anywhere without observations. We have the best models in the world. Without observations, they're pointless. What I think we can do for Cosmo right now are two things. One thing is we can come up with these methods for how we would use the data when we get this. This also applies to the DKIST, formerly known as ATST telescope, which will take measurements. We can come up with analysis techniques that would then use the data and fit to models in useful ways. So that's one thing we can do right now. Before it's built, we can start doing that, which will make our arguments stronger for going out and advocating for more funding, because that's ultimately what we need. We have to get money if we're going to build Cosmo. I think we have to build Cosmo because I think we're going to need these observations for space weather. But we have to make a bulletproof case, and I think we can do some work right now in terms of figuring out the analysis techniques to strengthen that. We also have telescopes in China, as I mentioned, that are coming up. We have COMP. COMP is going to be very useful for this analysis technique development that I'm talking about. We can start using COMP to test it. And it's already proved useful in terms of showing signatures of stored magnetic energy in the corona. So we have to use observations. Space missions. There's a lot of actually really exciting stuff going on. Because here's the thing, and I didn't really get into this because I kind of cut this part of the talk, but I honestly think the way we're going to have to do this is multi-wavelength. We have some wonderful observations in the infrared and the visible that we can take with Cosmo. There's a possibility for radio observations to get magnetic fields. And the thing is, each wavelength gives you a different sensitivity. If you go into space, you can look at the ultraviolet and the extreme ultraviolet. And I had a whole slide on this, but there's different diagnostics. They see different parts of the coronal magnetic field. Because, of course, you're seeing sort of all the stuff is getting integrated along your line of sight, and that's what you're seeing in your signal. The sensitivity of how it integrates changes with wavelength. And we could use that information. That's part of what we're planning to do with this approach, is to try to come up with techniques for making use of all the different wavelengths to come up with a solution. So Europeans have been talking a lot about this space. I don't know if it's actually going to go forward, but it might. But there's a lot of talking of something which would be measuring coronal magnetic fields with a space telescope, and I think we should be involved. I think Steve's probably been on various SOCs for that in the past, and we are, through this COST program, getting closer and closer to them. So I think that's one way forward for us in terms of an involvement in a space mission. In terms of the U.S. and NASA, I think this is an excellent idea for a small explorer to do some sort of coronal polarimetric observation coupled with ground-based observations. And I think we should join with the community on that. There are also proposals in action right now to do testing capabilities for this kind of space mission, explorer, using balloons. And so, again, I think Steve and I are both on that proposal, which has gone in again. And so there we are trying to make connections and work with the community, because these are important observations.
Now that the area of observations has been opened, are there any more questions on that? Well, I will ask one question. So, if you remove the realities of the budget environment, and for a moment I will allow you to dream and dream big. So how would the observing system of your desire look to remove one of the sticking points?
Oh yeah. Well, first of all, you need a coronal polarimeter looking in a range of wavelengths. In space, you need one at the Earth's orbit. You need one probably at something like an L5 orbit. So not only do you see, so you can see the CME structure as it leaves the limb, because those are the ones that are actually coming at us. You have a sequence of ground-based observations all around the world, building up, again, observations at multiple wavelengths. And then I think it's a slam dunk. We have the observations. The funding reality means we have to choose wisely about how we do this and how we actually implement it. But this is how we do it. And I think the off-Earth viewpoint is critical, not just for coronal polarimetry, but for space weather observations. And so that is pretty important.
If no more questions at this point, just when I say that, they might come up. With that, I would like to thank Sarah.